Alrighty. We're going to finish up with section 1-2 here. Like I said, the only two things we need to go over are absolute value and composite functions. And, okay, so what do you guys remember about absolute value? What is it? Yes? It looks like that. Yep, it looks like a big flying V when you graph it, but what is it? What does it do? You input a number into absolute value, and what does it do to it? It always makes it positive, okay? And the reason that absolute value always makes it positive is because the function of absolute value is to calculate the number's distance from 0. And distance is always positive, right? So if it's a positive number, it just returns the same number. If you give it a negative number, it'll turn it positive because that negative number is that distance away from 0, okay? So it measures distance from 0 and as a result always returns a positive number. My favorite function? No, not absolute value. My favorite basic function. I'm a big fan of the square root. Yeah, it's a good one. All right, another way to define absolute value then, usually we just write it, like with its symbol, f of x equals absolute value of x, like that. But because of its definition there, though, we can define absolute value as a piecewise function. And this is going to be important later on when we start talking about derivatives and things. So think about absolute value in two pieces, okay? So if the number that I'm inputting into it is something negative, it's following the function negative x. And if I input into it something positive, it's following the function just x. And that's why you get that flying V kind of look at the graph. It's really two linear functions put together, right? It's negative x as it comes down the one way, and then it's positive x as it goes back the other way. So it's really a combination of those two things. Now, where do you put 0 in here? Well, technically it doesn't matter. You could put 0 in either category and it would still work. So I think kind of the more accepted way of doing it would be it's negative x for x less than 0, and then positive x for x greater than or equal to 0. But technically the 0 could go either place. Okay. So, might ask you to sketch a graph of absolute value, or take a look at absolute value and an equation and draw a graph, or look at a graph, come up with its equation, that sort of thing, domain range, all that kind of business. So let's analyze an absolute value function here. So let's say we got f of x equals absolute value of x minus 3 plus 1. All right, and we need to, let's come up with the graph, find its domain, and find its range. Okay, so we're going to focus on those three things. So the graph of this, if we start with just what the graph of a regular absolute value looks like, this is simply just a transformation of that, right? It's had some movement. So all right, so a regular absolute value graph. I'll put a little color on here. So we said that, thinking about this little piecewise definition here, it's negative x as long as we are, oops, make this a little straighter. All right, so it's the function negative x if we're less than 0, and it's the function positive x if we're greater than 0. So it looks like that. So this new one, though, this x minus 3 plus 1, like I said, is a transformation of that. So how has that been transformed? Is it a stretch? Is it a shrink? Is it a shift, left, right, up, down? All right, so we have some shifting going on, right? So in what direction? Raise your hand maybe, and I will call on you then. Okay, Rachel, go ahead. Up 1. Okay, yep. And to the right 3. Good. Remember, if it's on the inside of the function, okay, then it's always the opposite of what the sign is. If it's on the kind of the outside, then that's going to be the same. So this is a right 3, up 1. So that means I'm just going to take this thing and translate it. So now, kind of like a parabola has a vertex, absolute value has a vertex. So a normal absolute value, or the parent function, has a vertex at 0, 0. The new vertex now is going to be at 3, 1. And then it's all the same from there. So it heads up that direction, and it heads up that direction like that. Okay, so that's your new one. So we're able to produce what the graph looks like there then. And then from that, we can do the domain and range pretty easily. Okay, now the domain. This is true of any absolute value function. Whether you stretched it, shrunk it, translated it, up, down, left, right, what should the domain always be? What numbers are okay to plug into an absolute value no matter what? It's all real numbers, negative infinity to infinity. Yep, all of them. Okay, remember with domain, there's only 3 kinds of functions that are going to give you any kind of something different than this. And that's if it's a reciprocal type function where you're dividing by 0, a square root because you can't take a square root of something negative, and logs because you can't log something negative or 0. Okay, so absolute value, domain, negative infinity to infinity, it's all of it. The range, that will be something different. And with the translation, it affects it as well. So look at the graph. What's the range here? 1 to infinity. Good. And do we include the 1? Yes, because it does actually get there. So my suggestion would be, because they're probably going to ask you for both domain and range here without a calculator, but knowing what you know about the absolute value graph, do the graph first, then you can easily answer the questions about that. Okay? If you try to go after the range without looking at what the graph is, it's going to be pretty hard. So, okay, good. Let's transition. We'll go on to composite functions next. Do a little review over those guys. So what do we remember about composite functions? What are those? Oops. There we go. Okay, so what do we remember about that? Everything. Good. So, tell us, Rachel. You might as well just teach the class. It's fine. No, what are they? What's a composite function? It includes multiple pieces. Yes, true. In what way? Do we need a little help? Yeah. Okay. F of g of x and g of f of x, that type of thing, those are composite functions. When you take one function and you substitute it into the other function for x. Okay, so for example, let's say f of x is x squared plus 2x and g of x is x minus 1. So then if I did f of g of x, okay, you can kind of see the substitution right in the nomenclature there. Or notation, I guess maybe is the better word. So then the g of x is going to be substituted into f of x for every x. So it would become then x minus 1 squared plus 2 times x minus 1. And then you could do some simplification from there if you wanted to, FOIL out the x minus 1 squared and distribute the 2 and all that business. But at the end of the day, though, that's still the composition f of g of x. And then you can go the other way with it, too. So if you wanted to do g of f of x, that would be taking the f function and substituting it into the g function everywhere you see an x. So we only have one x in the g function, so this entire thing, x squared plus 2x, would get dumped into x right there. So we'd end up with x squared plus 2x minus 1. Yeah, it would just look like that then. Okay. F of g of x and g of f of x will not necessarily come out to be the same thing. Sometimes they do. Most of the time they don't, though. Okay. So this is kind of a input-output type thing. Again, we're talking functions, right? So there's, if you're going to do f of g of a number or g of f of a number, it's a situation where the output from one function becomes the input for the next one. Okay? So if I wanted to find, let's say, f of g of 2, okay, a couple different ways I could go about doing that. If I wanted to go directly to my composite f of g of x, I could just plug a 2 directly into that and be done. Okay, crunch it out, see what I get. Otherwise, think of it this way. You're going to do 2 as an input into g, and you're going to get an output from g. And then that output from g becomes the input for f. So you got to figure out what's g of 2, and then use that number into x. So take a look at g of x. What is g of 2? 1, right? So f of g of 2 is the same thing as f of 1. Does that make sense? So that output that we got, 1 from g, is now our input for f. So f of 1. And then we can just look at the f function. Okay, what is f of 1? 1 squared plus 2 times 1. What do we get? 3. Okay, so that is 3. So think of things kind of that way, and I think it makes it a little bit easier when you're crunching numbers. Just while we're doing it, might as well go the other way too. So what is, let's say, g of f of 2 as well? Go the other way with it. So start with f now. Okay, we always kind of work inside out with these. So what is f of 2? 2 squared plus 2 times 2. 8. Okay. So that's going to leave us with g of 8. And if I plug an 8 into the g function, what's the answer then? 7. Yeah, 8 minus 1, 7. Okay, good. Let's see. I think that's all we need to do with those guys for now. We'll talk more about composites later, but I think we're good. I'm going to stop the recording.